Yeah, thanks, Brian. And also thanks to the Great Lakes Fish Commission staff for this incredible week of presentations on the fisheries in the Great Lakes. I mean, what a great session. I'll also say biologists are very good at making observations, noticing things in the environment. And I unfortunately wasn't here the entire week, but drove down late last night, and I could tell you the people that have been here all week versus those that show up, you can observe it. You guys have had a long week, so thank you for being patient. And little did you know, those that stayed for this session, you're going to have to hear me talk twice today. But I am glad to be here for Nick Legler, who has put this together with the Salmonid Working Group. Although I will say last night the Salmonid Working Group met, and at first we thought Brad Eggle was going to do the presentation, but then I thought, well, if Wisconsin wins, I'll do it. But if Wisconsin loses, I won't. And they won, so I guess I have to do it. But then Dave Clapp said, well, if Michigan State wins today, then he'll do it for me. I thought, I should take that bet. Well, the Salmonid Working Group, a vast number of people, the QFC is a key group. This really ties together a lot of efforts for Lake Michigan and the technical and the Lake Committee. Through the Salmonid Working Group, the Planktivore Working Group, the QFC, huge amount of effort. I have to also say that looking at the Salmonid Working Group and the history, and then hearing Dave Clapp talk about the Yellow Perch Task Group, it is amazing when you put together historical perspective of where these technical groups have come to and how much information is collected and how we use that information. So today I hope one thing to install is, wow, this is really an incredible process. The Salmonid Working Group had an old red flags analysis, which was really based on indicator and trend indicator variables, but really was also built on a lot of information in previous red flags or 10 red flags. Bottom line, how do we assess the predator-prey relationship in Lake Michigan? And how do we know when it's out of balance or when the predators are in balance with prey or not, which is one of the overall fish community objectives. So I'm not going to talk much about the history anymore, except to say this process was reviewed and replaced with the new predator-prey ratio, which we're going to report to for the first time officially as a working group activity. So what I mean by that is we had the old method reviewed, the predator-prey ratio was recommended as a new approach, and this was the first year we actually put it in motion. And last night at our working group meeting, somebody asked me, they said, well, we were talking about the pros and cons of doing the predator-prey ratio for the first time, and someone said, what did you think the process went? And I said, I'm surprised we actually pulled it off. I mean, this is a big process. It runs complicated models, and a lot of kudos to all the folks in the Salmonid Working Group and the data that went behind this. So what is the new predator-prey ratio? Basically, we have two indicators, a primary indicator that I'm going to talk at length about, but then also auxiliary indicators. The primary indicator is based on Chinook salmon biomass compared to alewife biomass, predator-prey ratio. The biomass of the predator compared to the biomass of the prey. But in order to estimate those, complex statistical catch-age models, predicting, taking all the data that we had. And what's nice about this is instead of the trend indicator where we have graph after graph after graph, it's now one graph, a ratio of predator to prey as an indicator. With any model, though, a good model, you should have ways to ground truth it. Is it really reflective of what's going on in the world? That's where the auxiliary indicators come to. So we'll go through each of these as well, just to say, does our prediction of the primary indicator, the predator-prey ratio, be supported by things like the primary or the auxiliary indicators? Quick depiction of what this will look like. Basically, the ratio is going to be a proportion, and it's going to range from 0 to about 0.1. And when the ratio is low, like 0.001, what that means is there's a lot of prey relative to the predator biomass. In contrast, when the ratio, and this is where it was early on when Chinook salmon, or alewife abundance was high, and we had, prior to introducing the salmonines or Chinook salmon. On the contrast, when Chinook salmon abundance is extremely high and prey is limited, you'll see the ratio approach a higher value of 0.1 or 0.009 or 0.08. That's the basic concept behind the ratio. with any model or analysis, one of the good things to do is to step back and apply it to previous data and see if it supports your understanding of what's going on. I'm not going to talk a lot about the retrospective analyses that have been done, but I'm going to talk about this graph a little bit to say that basically, if you look at this predator-prey ratio estimated up to this point in time, not 2014, just as a historical analysis, you can look at or start to see indicators where 10% of the predator biomass to prey biomass is an upper limit capacity of the system. In other words, if you have at any point in time 1 pound of salmon to every 10 pounds of alewife or less, the system can't sustain the predator biomass. And instead, what's really what you want is for every pound of salmon that's in the lake at a given point in time, you'd like to see a ratio of about 0.05, which means you need about 20 pounds of alewives or prey, their main prey, to support that salmon biomass. I'll back up. Today, we're not going to provide any management recommendations. So why are we here? What we do want to say, though, is the ratio itself is unique in that really you can look at this and compare yourself on a relative scale. If you want a sustainable salmon biomass to alewife, you don't want to be up here. And therefore, you probably should stock less if that's your primary management action. If you're down here where there's a lot of prey relative to the salmon biomass, you should stock more. So even though we're not providing a hard and fast management recommendation, you can use this ratio to gauge your stocking policy on a relative scale. Okay, so we're going to use the target of 0.05, the upper limit of 0.1, and look at how this matches up, this method, before we give it to other lakes, before we give you the ratio for 2014 for Lake Michigan. Rick Clark did a lot of this analysis, so if you have any questions afterwards, I might direct them to Rick. But basically, Rick used a Lake Huron Chinook salmon model, which is Jim Bentz and Travis Brendan put together, relative to the alewife collapse in 2006, and found the ratio was 0.11. So again, suggesting that's an upper limit not only for Lake Michigan Chinook salmon alewife, but really on a predator-prey relationship, almost any system, because we saw what happened after the ratio hit 0.11, the Chinook salmon population crashed. Also, if you look at Lake Ontario, this is from some published values applying the predator-prey ratio to that data. Lake Ontario is about 0.065, pretty close to its target, and you can see that they had relatively stable alewife and Chinook populations when they were near the target of 0.05. Okay. So let's look at now applying some more recent data to the Lake Michigan projection model. And the nice thing about the framework of having this in a predator-prey model with data is that you can actually then make predictions about where the ratio would go. So if we went back to this data point and we made predictions based on what we knew about fishery catch rates and alewife recruitment and salmon recruitment, and we project in the future, the projections here suggested a stocking cut might be needed because the ratio was approaching 0.1, and in which case it actually was. This led to stocking reductions that we've seen in the past, and now I kind of want to go forward to what is our predictions or estimate for this year and predictions into the future. Well, when we ran it last year, before we added the data, it looked like the predictions were that the ratio was going to approach 0.1, but then would start to decline. And we were feeling pretty good about adopting the method and applying this to the Lake Michigan, Lake Huron data. I'm sorry, Lake Michigan data. But then this Lake Huron issue started to arise. And what we found was that, as Matt just talked about, these fish just won't stay in the lake they're stocked. And the Lake Huron fish were moving over to Lake Michigan. So a big change between what was developed for the predator-prey ratio and what we implemented this year is that we're going to now account for the Lake Huron stocked fish moving into Lake Michigan. Stocked fish. What I want to also point out is we don't really have a good estimate of how many wild fish are born in Lake Huron and then move to Lake Michigan. But where we thought maybe the ratio is going to approach the target, you'll see now adding the Lake Huron fish really changes this equation. So the first step in calculating the ratios, run the biomass estimates. Put everything, all the data points into one model for both Chinook salmon, including fish stocked in northern Lake Huron, and then also alewives. And this is the net movement back and forth. So the prediction of the model is that the Chinook salmon biomass is going to increase, and here's the for the alewife biomass decreasing. And although you look at this ratio and you might say, this is really a Chinook salmon alewife ratio, I also want to point out that in order to run an adequate or appropriate alewife model, you need to account for consumption and consumption across the key predators, not just Chinook salmon. So the alewife model actually includes consumption by Chinook salmon, by lake trout, by coho salmon, by steelhead, and by brown trout. The ratio, however, what we're going to do is we're going to compare Chinook salmon biomass to alewife biomass, knowing that the consumption is adjusted for those other salmonids. So here is the 2014 estimate from this data, from the data. Again, now we have one indicator, one graph relative to targets. The predator-prey ratio for Lake Michigan, here's the trend. These yellow points are our stocking reductions. In 2013, when we added the Lake Huron data, we approached the 0.10. Again, this is the upper limit capacity of the system. In 2014, the ratio dropped to 0.07. The prediction now says it's going to increase next year and then decrease closer to the target based on the model projections. A couple things to point out about here. So again, we're not going to say the ratio is 0.07, therefore you need to do X. But it does give you a relative comparison of where you are from the target to the upper limit. Also, the model predictions. Any model prediction that you make will increase in uncertainty as time goes on. So we might be very good at predicting the weather today and tomorrow, but if you try to predict the weather a month from now, it becomes less certain. The same is going to apply to the predator-prey ratio in Lake Michigan. The more that you predict, the uncertainty will increase dramatically. And again, these are short-lived species. Chinook salmon, 3 to 4 years in the lake at maximum. So to make predictions out 5 years is somewhat using the model and the law of averages, but our uncertainty around those estimates will increase dramatically. So what does this mean now, 0.07? Does that mean that the prey fish populations are recovering? Does that mean our stocking cut in 2013 actually had an impact on salmon biomass enough to bring the ratio down? And then how confident are we in the predictions going forward? Well, to look at that, that's where the auxiliary indicators come in. That's where we ground truth these model predictions with the predator-prey ratio. And the first one I want to talk about is the standard weight of 35-inch Chinook salmon. So basically this indicator is, it's kind of like a condition indicator. You're looking at the weight of a Chinook salmon at 35 inches. And as prey populations decline, the weight declines. And this is a predicted, so it's but it's based on a lot of empirical data on raw fish data. As the weight increases, then it suggests that the predator-prey ratio is more favorable in terms of more prey to predators. The red, in comparison, is Lake Huron. So the Lake Huron, suggesting this auxiliary indicator suggested that the prey base was being stressed. In Lake Michigan, we saw that decline, not as dramatic, some variation in the last time, but from 2013 to 2014, we saw a decline in the weight of a 35-inch fish, suggesting that that predator-prey ratio being above the average makes sense. If you look at this across jurisdictions, pretty good comparison across the different jurisdictions, so not much to say except this is lake-wide data. One of the criticisms or shortcomings of the old red flags methods was a lot of it was based on one agency or one jurisdiction. And these models now incorporate lake-wide data from catch to creel to weir returns across the lake. So it's good to look at whether or not we're seeing variation. But if anything, it looks like we're seeing a tighter fit across the jurisdictions as one salmon population. How about auxiliary indicator number 2, the targeted boat catch rates in the Lake Michigan charter fishery? Before I showed you this, I should have set it up a little bit and said, well, if the predator-prey ratio is coming down, shouldn't the catch rates come down? Shouldn't, if there's fewer salmon relative to the prey base, it should mean that the catch rates decline. And in fact, the catch rates have declined. They came up a little bit from 2013 to 2014, but they've declined a lot more than what the ratio is actually predicting. That's suggesting then, when we get to it, there should be fewer alewives. So the salmon population came down, but so did the alewife population. The lake wide is 0.13 fish per hour. And if you look at it across jurisdictions, I was actually kind of surprised by this. Pretty good fit between the Wisconsin and Michigan fisheries, where in the past we have seen some variability. And I think this might be more variability in our estimates of creel, or I'm sorry, charter catch rates than it actually is in the trends. But again, pretty big declines in the charter catch rates of Chinook salmon in 2013 and 2014. So another auxiliary indicator then would be the weir returns. So there are the weir returns suggesting that the average weight of a 3-year-old Chinook salmon is also declining, and we see that decline going here as well. So even though salmon abundance declined, it supports the idea that alewife biomass must be decreasing, keeping that ratio above 0.07. By the way, it's 14.9 pounds is the 2014 average. If you look at across weirs, again, it's interesting because you kind of see a lot of variability early in the time series, and then more fit or similarities in the recent time series. But most of the weirs declines in the weight of a 3-year-old fish. Another auxiliary indicator could be, well, what happens if the predator-prey ratio is right on target, but the entire lake is full of only Chinook salmon? Or that the fishery isn't diverse, because our fish community objectives call for a diverse salmonine fishery. And what we see is actually the Chinook salmon proportion in the harvest has been decreasing over time, closer to that 50-50 split for the fish community objectives. And other salmonines, such as lake trout, here in purple, have been increasing over time. Steelhead and coho salmon, relatively consistent. So more of a lake community index, again, supporting the idea that the predator-prey ratio is describing well what's going on. The QFC also helped us develop an index with the fish community objective that's based on the idea that these fish community objectives were developed at a time in the Lake Michigan fish community when there were a lot of alewives, and the catch rates were very, very high. And our targets, therefore, should be based on, or could be based on, what the expectation is in the fishery. This FCO target is a relative scale that basically uses our stocking policies and the catch rates as indexed to the 1980s period to say where we're at relative to the fish community objectives. So when we're near this blue line, we're near our fish community objective targets. This is below and this is above, and basically these are suggesting that the salmon population is coming down closer to our fish community objectives, and projections suggest that we're there. Okay, auxiliary indicator number 6. If the ratio is 0.07, and we know from the fishery catch rates that the Chinook population has declined substantially, then this would have to mean that the alewife population also must be coming down. Another way, besides looking at lake-wide biomass of alewives, would be a truncated alewife composition. In other words, decrease in the number of year classes present in the alewife population. This is from USGS data. Bo presented this yesterday, and it basically suggests that, we're not seeing many alewives over age 5. We're not seeing many over 180 millimeters. The abundance of large, older alewife has been declining, again, supporting the idea that even though the stocking cut and the reduction in wild recruitment has driven down salmon populations, the alewife populations have also declined and are still, and this truncated age composition is relatively concerning. Okay, so let's talk just a little bit about putting this in a bigger context, and how do we use it? How does the Lake Committee use it? How do we communicate this to the public? And in overall, what does it mean for the salmon fishery in 2015? Well, although we don't have a written report out on the table today, we do have a draft report that will describe both the methods and this analysis. Contact myself or Nick or anybody in the Salmonid Working Group. We should have this completed relatively soon and for public distribution. But also, let's put this in the context of management action. So how to use this information, how do managers use this information to adjust stocking policies or harvest policies? There was a series of public meetings that led into this, and when this last stocking cut was made in 2013, which is a lake-wide Chinook salmon stocking cut by 50%, it was decided that the best thing was to have a feedback policy that says if we need to cut stocking because Chinook salmon are too abundant and the prey base is down, when do we change our policy? And so, in lack of a better indicator, this is kind of before this predator prey was adopted, the lake committee decided to use a weight of an age 3 fish returning to the Strawberry Creek weir as the indicator. So I'd like to show you where we're at with this, even though we're suggesting the predator-prey ratio is a much more robust method. But if the ratio is saying we're 0.07, we're not at that upper limit, what does this compare to the index here? What I also want to say is part of the reason why they chose this data set was these are all known age fish. The data quality is extremely high, so it might be limited in spatial scale, but it's very good in terms of its quality and confidence in the estimate. So let's look at the Strawberry Creek weir. A lot of text here, but what I'm going to break it down is basically the weight of a 3-year-old fish returning to the weir should be between 7 and 9 kilograms. If it's below 7 kilograms or below 15 pounds, then that means that the fish are too small, there's not enough prey, you'd cut stocking more. If the fish are over 9 kilograms or 20 pounds, then that would suggest that there's a lot of prey, too many salmon, increased stocking. And this was supposed to be conducted in a 3-year average. So where are we at relative to this indicator? Here's the Strawberry Creek weir facility. And again, this is a highly controlled. These fish are, many of them are quota wire tagged, like there's very little error in the data. So just put this up over time. What you can see is the weight of a 3-year-old fish increased, then prey base declined, the weight declined. And since then we've seen an increase actually in the weight of an age 3 fish, suggesting that the ratio is starting to get better. And if you look at the targets, the 15 pounds versus 19 pounds, and you run a 3-year average, by the way, 8 out of 11 years were below, so we had a period of, where are these stocking cuts that we listed before? That was right there in that period. And basically what we see is that in the last 3 years, when we run the average, the value is 7.23. So if we didn't have the predator-prey ratio, we were using the original feedback policy adopted by the Lake Committee, we would have status quo stocking policies. And that's what this says right here. All right, so overall, I mean, there's a number of people in the room that have contributed to this data in the Salmonid Working Group. If I missed something on behalf of Nick or the group, please feel free to join in. The recommendation, or again, the analysis suggests that the predator-prey ratio has declined, still above our target, but well below the upper limit. And the stocking policy, this is probably more my opinion than the group's maybe, but the stocking policy in 2013 to cut lake-wide stocking by 50% had an impact and likely avoided a full crash in the salmonid population, in addition to the decline in wild recruitment, as mentioned by Matt, concurrent with our stocking reduction. So Mother Nature got the memo or something, I don't know what happened, but wild recruitment and stocking went down dramatically, the ratio dropped. The predictions in the future are next year the ratio is going to increase again, suggesting that without some alewife recruitment, the ratio will probably continue to increase. But right now the current stocking policy is within the guides, both for the predator-prey ratio and for the weight of an age 3 fish at Strawberry Creek. So with that, I'll take any questions and thank you guys for your time.